Hi students, welcome back to our problem solving series. In this video, we'll tackle the problem of inverting a binary tree. Okay, before we dive into the solution, let's understand the problem first. So, the problem statement says we are given the root of a binary tree and we have to invert the tree and return the new root. Okay, so for example, if the given input is like this, the tree representation of it is this way, we have to return the invert or the mirror image of the tree. Invert is nothing but all the left childs become right and right childs become left. So if you understand the definition of binary tree is nothing but a hierarchical data structure or a tree data structure which can have up to two children. They are often referred to as left child and right child. So when you mirror it, a right child becomes left child and a left child becomes right child. Okay. Let's look at the solution through a example. Let's say we are given this tree. Okay. Now to invert it, let's use a recursive approach first. So we will start at root node, which is this one. So at this node, okay, at this node we will swap the right and left child. Okay. So this becomes 4, 7, 2. Okay, we swap the right and left child, so the its children continue to be the same. Okay, now after first iteration, this is how it would be. Okay, so we start at root, we swap the left and right child. After that, in the recursive approach, what we will do is we will apply the same logic on each of the children. Here, since it's a binary tree, there are only two children, 7 and 2. So on the children, if we apply the same logic, what happens is, first let's consider 7. So here this is already reversed. So this is 7 and 2. Now at 7, we invert the left and right child. So left becomes 9, right becomes 6. Similarly, we do the same thing at 3. Okay. Now we follow the same approach to its children, which are 9, 6, 3 and 1. Okay. So when we are looking at the children, these children are nothing but, there is nothing basically, which is they are null. So when you interchange them also, it will still be the same. So this is our final tree. So when we reach a node which is null, we just return it. That is our condition where we break the recursion. Okay, so let's go through it one more time. We start at root, invert its children, then apply the recursion on each of the children. The moment we reach a node which is null, we break. Okay, let's try and write code for this approach. Okay, so here we are given a tree node definition which is like this, which has a left child and right child, and we are supposed to invert it. So in recursion, right, the condition at which you break the recursion is very important, otherwise it is very easy to go into a stack overflow error. So first let's write that. So if root equal to null, that is when we break, right? So what do? We return null. So when will root equal to null? In this case, when we are processing 9, uh, we try to do the recursion over its children, which is both nulls. Since it is null, we will break. We won't go any further. Okay. So it's similar for all of its children, not just 9. Okay. Now let's come to the actual logic. What do? We have to swap it. And swap, whenever we swap, we create a temporary variable, right? So let's create a temporary variable. Now make the left right. So we have copy of left in temp. Use that. And simply iterate over the left tree or recurse over the left tree and recurse over the right tree. At the end, what do we return? We return the root. Every time we have to return the root of whatever we are processing. Okay, let's submit this solution. Yeah, so it ran fine. Let's see the time and space complexity of this approach. Time complexity, we are traversing each and every node. So it is order of n, where n is the number of nodes. In case of recursion, right, space complexity becomes a bit tricky. Here, if you see, we are going to each of the left and right child. Okay, so in the worst case, let's say the tree has only left child or only right child, which is essentially a linked list in a way. Then the space complexity would be order of n, because we have to go one by one, one by one. But in the average case, if the tree is balanced, we only go to the order of log n, which is size of the tree, height of the tree. So this is worst case, whereas average case is order of log n. So we basically traverse or recurse as long as the height of the tree. So our space complexity is height of the tree, which is nothing but log n. Okay, but worst case complexity is what we report, so it's essentially order of n. So this demonstrates the power of recursion. If you can just imagine the solution in a recursive way, it is very simple to write. See, if you see the code, it's just few lines. Okay. So let's also look at a iterative approach for this problem. Let's look at it through another example. Let's say this is the tree we have now. So in this case, in the iterative case, so in recursion, we were in a way storing everything in the call stack, right? So in the iterative approach, we will have to have some such data structure which holds our nodes. Let's use a queue. Okay, queue. So initially, if the boundary condition is still the same, if the root is null, we just return because there is nothing to process. So when we start at the start of the tree, okay, we add the root to the queue. Okay, then so now one is added to the queue. So as long as the queue is not empty, we take an element from the queue. So in the first iteration, what is our current node? Our current node will be 1. So we pull this element from the queue and we swap its children. So this becomes 1, 2, 3, and their children continue. Okay, 2, 5, and 4. Then to further process these children, we add any non-null children to the queue. So in this case, we have 2 and 3. Okay. Then we go to the next iteration. In the next iteration, what do? We again poll the first element. So now the current becomes 2. Okay. So now we will again swap its children, which would be 1, 2, 4, and 5. Okay. Since we polled 2, this is gone. And now we add its children for further processing. Okay. 4 and 5. And the right child is still the same. Okay. Then when we pick up 3, we process its children. Okay. So this becomes 1, 2, 3, 4, 5, and we are currently processing 3, right? So 3's children get reversed or inverted and it becomes like this. And we add 3's children to the queue. Okay. At this point, then we will pop 4 from the queue. 4 has no children, nothing to reverse. Then we will pop 5 from the queue. 5 has no children. Then we will pop 6 from the queue. 6 has no children. And our queue is empty. At this point, we break. This is the iterative approach. Let's write code for the iterative approach as well. Okay, so let's reset it. Okay, now our boundary condition is still the same. If root equal to null, return null. Okay, otherwise we create a queue. Queue equal to new linked list. Linked list has a queue implementation. We are just using it. Queue dot offer, which is nothing but adding to the queue. We add root element. How long do we process? As long as the queue is not empty. While queue is not empty, what do? We take the current element, which is, let's just call it current, which is queue dot poll, and we swap its children. So to swap, we will again need a temp node. Current dot left equal to current dot right, current dot right equal to temp. Okay, so now we have swapped. What do? If current dot left is not null, okay, we add it to the queue. Queue dot offer current dot left. Okay, similarly we do the same for right. Current dot right, current dot right. Okay, so at the end of it, we just return the root. So here q dot poll is a function. Yeah, let's submit and see. So it also ran in quite faster. So what is the time complexity of this approach? Time complexity is we are still traversing all the roads, so it is still order of n. What is the space complexity? So space complexity is nothing but how big the queue grows. Queue grows as big as the number of children at that level. So if m is the maximum number of children at that level, it can be order of n. Okay, so while recursive solutions are simpler and elegant, they have a function called overhead. Iterative solutions give us a predictable space usage. Hence, for every for a very large input, iterative might be preferred. Okay, thank you for joining me in solving this problem. If you found this video helpful, don't forget to like and subscribe. Keep coding and keep challenging yourself. If you have any questions, please leave a comment on the video. Remember, practice makes perfect. So keep coding and improving your problem solving skills. Happy coding!